So the last type of special circuit that we're going to look at is the LC circuit. And this only contains a capacitor and an inductor. So we start out with the capacitor fully charged. So you can see as positive charges and negative charges on its plates, and there's an electric field in between them. So the capacitor is going to begin to discharge. So since the higher potential is over here, the current is going to go this way, counterclockwise, around the circuit. So we know that as the capacitor discharges, the current is going to increase, but the inductor is going to slow down the increase of the current. So as the current is increasing, the inductor is storing energy inside its magnetic field. And at the point when the capacitor is fully discharged, there's no more charge left on either of its plates, then the energy in the inductor is going to reach a maximum. And so is the current. The current is going to reach its maximum value, which we'll denote with I subscript m. So after this point, the capacitor is going to be charging again. As the current reaches here, now there'll be positive charges over here on this plate and negative charges on this plate. So the capacitor is being charged, but with the opposite direction, sort of, as it was initially. And so the current's going to start to decrease from its maximum value. And we know that when the current decreases, the inductor is going to slow down the decrease of current by releasing the energy it stored up. So then eventually, the capacitor is fully charged again, but with opposite sides. The plates have the opposite charge that they did initially. So the electric field is pointing the other way, and now the inductor has lost all of its energy again. Well, now the same thing's going to happen. The capacitor is going to start to discharge in the opposite direction this time. The current is going to go clockwise around the circuit, and then the inductor is going to start storing energy in its magnetic field, and at some point the current is going to reach its maximum value again, but in the opposite direction, and all of the energy will be stored in the inductor's magnetic field. And then the process begins to repeat. Now the capacitor will begin to charge with the same direction that it was charged initially. And so this process keeps repeating and repeating indefinitely, since there is no resistance. There's no resistor in the circuit. And so we have a case of electrical oscillation. So if we apply the loop rule to this circuit, then we get negative L di dt, which is the inductor, and minus Q over C, which is the potential difference across a capacitor. And this is equal to 0. And then we can solve for di dt, which is negative 1 over LC times Q, the charge on the capacitor. But remember that current is dq dt, the rate of change of the charge. And so we can write di dt as the second derivative with respect to time of q. So we get d squared q over dt squared, this should be a squared, equals negative 1 over LC times q. And this looks similar to the equation for simple harmonic motion. If you remember, that equation was d squared x dt squared, which is the acceleration, is equal to negative omega squared times x, where omega, remember, was the angular frequency, which is square root k over m. And so the second derivative of x with respect to t was equal to negative k over m times x. And so comparing this equation for simple harmonic motion with this equation that we just got from this LC circuit, we can see that the charge is analogous to the displacement, and this omega is going to be equal to the square root of 1 over LC. So we have a case of basically simple harmonic motion, but with a circuit. And so the angular frequency omega of the circuit is the square root of 1 over the inductance times the capacitance. And then if we want an equation for the charge as a function of time, well, we look at the equation for displacement in simple harmonic motion, which is x is equal to the amplitude times cosine of omega t plus the phase angle. And so an analogous equation, since Q, the charge on the capacitor, is similar to the displacement, we can write Q is equal to the maximum Q, which is the Q on the capacitor when it's fully charged. This is analogous to the amplitude times cosine of omega t plus the phase angle. And remember, the phase angle is something we use if the charge does not start at its maximum. As you can see in this case, when t equals 0, it's cosine of 0, which is 1, so Q is equal to the maximum charge initially, which is the situation that we described over here. And so in terms of energy, in an LC circuit, the energy is transferring between the capacitor and the inductor. So the total energy in the circuit is staying constant, and it's always equal to 1/2 Li squared, the energy in the inductor, plus 1/2 Q squared over C, the energy in the capacitor. So you can see it's being switched. The energy is being switched between the capacitor's electric field and the inductor's magnetic field. And it's going back and forth, and for the maximum energy, the total energy in the circuit, we can write two expressions. One, when all the energy is in the capacitor, that's 1/2 big Q, which is the maximum charge squared, over C. And when all the energy is in the inductor, it's 1/2 L maximum current squared. And so one last time, here's the comparison between simple harmonic motion and the LC circuit. You can see all the equations are basically the same, except the charge is replacing the displacement.